Okay, unsigned numbers are used to represent positive numbers, but if we need to work with negative numbers, we need to have signed numbers as well. Okay, so today we are going to discuss signed numbers. Usually we discuss the signed numbers in base 2, in binary mode, in base 2, because base 2 is the language that a computer understands, and we are going to discuss these signed numbers in base 2, and in base 2 is consists of zeros and ones, okay, and in order to determine the sign of the number, we always use or allocate the high order bit, which is the leftmost bit, high order bit for the sign. So high order bit is to determine the sign of the number, not the value of the number. Okay, so let's have a simple example. Let's say we talking about unsigned number. In unsigned number, if we have this number 1100 in base 2, and we want to see what's the value of this number in base 10. Okay, it's simple. We know that this one will be 2 to the power of 0. This one is 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3, because these two have 1. So we say 8 plus 4 is equal to 12. So the number 1100 in base 2 is equal to 12 in base 10. Any question? It's simple. We already learned it in the lecture. Okay, so but in signed numbers, if we have this value, we cannot say that it is equal to 12. Why? Because the high order bit is not part of the number. It's only dedicated for the sign of the number. So the value of the number will be determined by these 3 bits, the value, and the sign of the number will be determined by the high order bit. Any question? Okay, so we have three different ways to represent numbers in signed representation. So the first one is sine magnitude. The second one is ones complement. And we have twos complement methods, and we have one more methods that we will discuss later, but for now let's focus on these three methods. Okay, so first let's start with sine magnitude. In sine magnitude, if the leftmost bit, is 0, the number is positive. If the leftmost bit is 1, the number is negative. That's it. Okay, simple. So if the leftmost bit is 0, the number is positive. If leftmost bit is 1, the number is negative. Let's represent a number. Let's say we want to use 8 bits to show positive 3 and negative 3 in sine magnitude. Okay, 8 bits. So we know that 3 is 1, 1, 0, 0, 0, 0, 0, and 0. Okay, so these 8 bits, of course, these two ones on the right is equal to 2 to the power of 0 plus 2 to the power of 1 is equal to 3, and the rest of them are 0. We keep the leftmost bit for sign, just for sign, not for the value. So positive 3 is 0, 0, 0, 0, 0, 0, 1, 1, and negative 3 has the same magnitude, but the sign is different. Is it clear? So the sign is clear. So that one, the first one is 3, and the second one is negative 3. Okay, so what if we want to add or subtract these numbers, and is the sign magnitude the best method to represent negative numbers or no? The first thing I want to tell you is adding two simple bits. Okay, addition of two simple bits. So we know that in base 2, 0 plus 0 is equal to 0. 0 plus 1 is equal to 1. 1 plus 0 is equal to 1. And 1 plus 1 is equal to 10. Okay, it's equal to 10. Or if we want to talk in base 10, it's equal to 2. Okay, it's the way we represent the numbers. Now I have a problem here. The first problem, let's see. We know that in base 10, positive 3 plus negative 3 is equal to 0. Of course, we all know 3 plus minus 3 is equal to 0. But in the sign magnitude method, positive 3 was equal to 0, 0, 0, 0, 0, 1, 1, and negative 3 was 0, 0, 0, 0, 0, 1, 1. If we add them together, the result will be 0, 1, 1, 0, 0, 0, 0, 1. Is this number equal to 0? Of course, no. So we see that by adding just these two numbers together, the result is not equal to 0. Okay, so we should consider this problem for sign magnitude method. And before move to the so what if we want to subtract or add numbers? Before I continue, let me tell you one thing. This one is 3 in base 2. This one is 3. This one is 3. This one is 3. Okay, no matter how many zeros we have on the left. Okay, so the left zeros are ignored. So the left zeros are ignored. So all of them have the value of 3. Okay, so if I ask you to write number 3 with 4 bits, you say 0, 0, 1, 1. If I ask you to write 3 in 8 bits, you say 0, 0, 0, 0, 0, 0, 1, 1. Okay, so no matter how many zeros we have on the left. Okay, so now we want to add or subtract two numbers, two numbers together in base in sine magnitude. In sine magnitude, let's add two numbers. We want to add, let's say which number. Just let's add two positive numbers first. 75 plus 46. 75 plus 46. Both of these numbers are positive. And no, I don't want to have this number. Let me change it. Okay, let's go. Not bad. Okay, 75. 75, if we convert it to binary number, it will be equal to 1 1 0 1 0 0 1, and of course we have a 0 here, and 46 is 0 1 1 1 0 1 0 0. If we add these two numbers together, 1 and 1 is 1, 1 and 0, sorry. 1 and 1 is 0, we have a caveat. 1 and 1 is 0, we have a caveat. 1 and 1 then 1 is 1, we have a caveat. 1 and 0 is 1. 0 and 1 is 1. 1 and 0 is 1, and this one is 0. So this one is like the addition for two positive signed number. Addition for two positive signed number. Okay. But we know that we see that we don't have any caveat here. The caveat was equal to 0. Okay, caveat was equal to 0. So the result is correct. Because we don't have any caveat, the result is correct. So in sine magnitude, if we have a caveat, the result is wrong. Okay, so it means that the result is bigger than the range that can be represented with these like bits. For example, with 8 bits, we know that the leftmost bit will be reserved for the sign. So we can use 7 bits to represent the value. 7 bits. What's the biggest number that can be represented with 7 bits? Okay, the biggest number that can be represented by 7 bit is equal to 2 to the power of 7. 2 to the power of 7 is equal to 128. 128. So if the result is equal less than 128, okay, not equal, less than. If the result is less than 128, the result is correct. Here, 75 plus 46, what is the result? Is it less than 128 or no? Of course, 5 and 6 is 1, and 121. The result is 121. 121 is less than 128, so the result is correct, and it's the reason that we don't have any caveat. Okay, let's show an example that we do have a caveat and the result is not correct. Okay, so I'm going to do one more example. Let's say we want to have 107 with 46. 107 with 46 in signed magnitude. Okay, 107 is 0, 1, 1. This 0, I put it separate because it's a signed bit, okay? So we cannot consider it as number. 1, 1, 0, 1, 0, 1, 1. And 46 is 0, 1, 0, 1, 1, 1, 0. If we add these two numbers, we will have 1, 1, no, no, 1, 0, 0, 1, 1, 0, 0. But here we have a carryout. Okay, so we have carry out. So the result shown here, it's not correct. It means that we are out of the range. If we look, 107 plus 46 is greater than 128. Okay, so we have a carryout. So you may ask why we don't like apply this carryout to these two bits and change this bit to 1. What's the problem? There is a big problem here because the leftmost bit is not like this, it's not supposed to be used for magnitude. So if we do this, the number we got will be a negative number. The number will be, let's say the number will be 100110001. This is a negative number based on sign magnitude. What we know that the answer of addition of two positive numbers is definitely is a positive number. So we cannot like apply the carryout to the sign bit. Okay, any question? Okay, so the same thing for subtraction. For the subtraction, it's like we do the subtraction in base 2 in the same way we subtract with like with pen and pen and paper. So how we can do that? Let's have an example. Let's say we have 46 and we want to add it with negative 25 or subtract them. How we can do that? It's the way. The first thing we write 46. 46 in sign magnitude is, this one is a sign bit, 0, 1, 0, 1, 1, 1, 0. Negative 25, this one is 25, 0, 0, 1, 1, 0, 0, 1. Because it's negative, we put 1 here. So we want to add these two numbers. Okay, so please be careful. These two bits are sign bits, not the amplitude. Okay, so we want to subtract them. Because we want to subtract, we do like we know like how to subtract in base 10. So 0 minus 1, we need to borrow from this bit. So this one will be 0, this one will be 2, 2 or 10. Okay, so depends to if we talking base 10 or base 2. So 10 minus 1 is 1, 0 minus 1 is 0, 1 minus 0 is 0. No, sorry, 1 minus 0 is 1. 1 minus 1 is 0. 0 minus 1, we borrow is 1. So 10 minus 1 is 1. 0 minus 0 is 0. 0 minus 0 is 0. So this one is the subtraction. And what is the sign? What is the sign here? We look to the two numbers and we apply the sign of the bigger number. Which one has a bigger amplitude, 46 or 25? Of course 46, regardless of the positive or negative, just absolute value. Which one is bigger, 46 or 25? Of course 46. 46 is positive or negative? 46 is positive. So we consider positive. So this one is the answer. Okay, so we did like the subtraction. Any question? Okay, some problems for this system. The first one was when we add 3 and negative 3, the result was not equal to 0. The second problem, when we, not problem, the second issue or the complexity is we know we need like a hardware, complicated hardware to perform the subtraction. Okay, we need to subtract and add. So we need a separate hardware for addition and separate hardware for subtraction, but we don't want to have two different hardwares for performing addition and subtraction, because we know that both have the same basis, subtraction and addition. And the third like issue is in sign magnitude, we have two representations for 0. So this one is 0 and this one is 0. We know that positive negative 0 is equal to 0. So we have two representations for 0. We don't like it, okay? We want to have one representation for each number, not two representations. Okay, so here we like introduce the complement system to get rid of these issues. So we introduce complement system, which is one's complement and two complements. What is the biggest advantage of complement system? They eliminate the need for subtraction. They eliminate the need for subtraction. You saw that for sine magnitude, we had to subtract, like we subtract bit by bitwise, bit by bit by. But we don't want to have to subtract. We want just to add numbers. Regardless of positive or negative numbers, we want to be able to add them. So we want to perform subtraction by addition. Just by performing add, we get the subtraction as well. So I will show you how. So in complement systems, I said we have two systems. The first one is one's complement. Okay, so how does this system work? It's simple. Positive 3 was equal to 0, 0, 0, 0, 0, 0, 1, 1. Do you remember? Okay. In one's complement, negative 3, we complement all the bits one by one to get negative 3. Okay? So, negative 3 will be 1, 1, 1, 1, 1, 1, 0, 0. So, in one's complement, the 3 is this one, negative 3 is this one. That's it. Just complement like all bits of a number to get the need for, just to get the complement. Okay, so do you remember I said we can eliminate the need for subtraction by introducing the complement numbers? Let me show you. Okay, let me show you. Let's say we have two numbers. We have 48 and negative 19. We want to subtract these numbers, so 48 and or add these two numbers, no matter. We can say 48 minus 19, subtract 48 from 90, or we can say add 48 and negative 90. Okay, so 48, of course, is 0, 0, 1, 1, 0, 0, 0, 0. This one is 48. Negative 90. What is the negative 19? In order to find negative 19, first we need to find 19 and then complement the bits. Okay, so let's do that here. 19 is equal to 0, 0, 0, 1, 0, 0, 1, 1. So this one is 19. In 1's complement, negative number 19 will be 1, 1, 1, 0, 1, 1, 0, 0. So this one is negative 19. Okay? So we say negative number 19 is 1, 1, 1, 0, 1, 1, 0, 0. This one is negative 19. And all we need to do for this subtraction, just add these two numbers. We don't have to subtract like what we did here in sine magnitude. The only thing we need to do is add these two numbers, okay, these numbers. So if we add them, it will be 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, and we have a carryout here. If we have a carryout, the carry bit is carried around and added to the sum. So we bring it here and add it to the sum. If we have a carryout, the bit is carried around and added to the sum. So we will have 0, 1, 0, 1, 1, 1, 0, 0, 0. And this one is the answer. So this one is the solution. You see, the only thing we did here, it was addition. We added these two numbers. There was a carryout. We just carried around and again add the carryout with the sum and we got the result. So the only operation that we performed was addition. We didn't do any subtraction, but we subtracted these two numbers by addition. Is it clear? Any question? No question? Okay. What if there is no carryout? That's fine. So we don't need to add it. Okay. It's very good. Okay, it's very good, but still kind of problematic. What is the issue? The issue is the first issue is we need to have an extra hardware or extra the hardware to add this carryout with the sum. Okay, so it adds some complexity. And again, we do have two representations for 0. So positive 0 is 0, 0, 0, 0, 0, 0, 0, 0, and negative 0 is 1, 1, 1, 1, 1, 1, 1, 1. Still, we have two representations for 0. We have some complexity for addition because we need to carry it around and add the carryout to the sum. But the advantage, we got rid of subtraction. Okay, we just perform addition to add two numbers. Any question? Okay. Now, so we had three problems. One, the first problem was subtraction. The second problem was two zeros. Third problem was complexity. Okay, so by introducing one's complement, we solve the subtraction problem, but still we have these two problems, and we want to see if we can solve it or no by introducing a better complement system. Another complement system, which is the best one, is two's complement. Okay, two's complement. Okay, so if the number is positive, just convert it to binary. So nothing, just positive number is positive. So sine magnitude, one's complement, two's complement, all of them, positive numbers are same. Okay, so if the number is positive, two's complement is similar to sine magnitude and one's complement. But if the number is negative, we find one's complement and then add 1. So we find one's complement and then add 1. So we have the two's complement. So if x was the number, one's complement was x bar. Bar means the complement. Okay, I don't know if I mentioned it before or no. If not, let me tell you. If we have 1 0, okay, if we have 1 0, 1 0 bar is equal to 0 1. Okay, the bar means complement. Okay, so bar means complement. Or we have another way to represent is prime. So 1 0 prime is 0 1. Both of them, this prime and this bar, they have both have same meaning. Okay, so in one's complement we just complement bit by bit, but in two's complement we complement the number and add 1. Okay, and now all problems are gone. Okay, so we don't need to worry about the addition, subtraction, we don't need to worry about the complexity, we don't need to worry about two zeros. Why? Because regarding zeros, let's see, 0 0 0 0 0 0 0 0 is positive 0. What is negative 0? For negative 0, we need to complement it and add it by 1. Let's complement it. 1 1 1 1 1 1 1 1 plus 1. The result is 0 0 0 0 0 0 0 0. You see? So both negative 1 and negative 0 and positive 0 are same. Okay, so it's this problem is also gone. We don't have any problem with two zeros. Of course, we don't need subtraction, and we just need to simply add two numbers and ignore the carryout if the result is in a range. I will talk about the range for different methods in the next lecture, but here just let me show you an example. We want to subtract 48 from negative 19, or add 48 and negative 19. So 48, of course, is 0 0 1 1 0 0 0 0. This one is 48. And negative 19, okay, so as we did for a previous example, 19 was equal to 0, 0, 0, 1, 0, 0, 1, 1. So negative 19 is 1, 1, 1, 0, 1, 1, 0, 0 plus 1 is 1, 0, 1, 1, 0, 1, 1, 1. So this one is negative 19. Okay, so negative 19 is 1, 1, 1, 0, 1, 1, 0, 1. And we add these two numbers, we will have 1, 0, 1, 1, 1, 0, 0, 0, and we have a carry out 1. Okay, so what about this carry out? We simply ignore it. We simply ignore it. Okay, we don't need to carry it around, and we simply ignore it. If the result is in the range, definitely the answer should be correct. Okay, so this number of course is 1, this one is 4, this one is 8, and this one is 16. So 16 plus 8 plus 4 plus 1 is 24, 25, 29. 29, yes, 29. And we know that definitely 48 minus 19 is 29. And the number is positive.